Okay, so last we left off, we were kind of talking about isotopes. So what is an isotope again? Isotope. Can you hear me?
Yeah.
Do you guys see my screen? What's on the screen right now?
The screen says max spectrum of neon.
Excellent. Okay, so what is an isotope?
An isotope is when a certain chemical or like a certain element has more weight.
Okay, so a certain element has more weight than what?
And more like basically because it has more weight, that means it has like extra electrons or neutrons.
Is it extra electron?
Proton.
No, protons. No.
Protons. Okay, good. Okay, so if you take a look at here, this is basically three different isotopes of neon, right? This gives us the relative abundance of neon. So if we take a look at this guy's of what? Probably like 90, what, 94, 95%. So neon, this is neon 20. This here is about, I'm gonna say, well, actually, that looks more like 90, maybe. Let's see. Yeah. Let's say 92, roughly. So I'm going to say this guy is going to be about maybe 6. And then this guy is going to be 2. Okay, roughly 2%. So one isotope, we have about isotope 20, neon 20. We have about 92%. This guy, we have about 2%. And then this guy, we have about 6%. Okay, so now this is what they see in nature. Right? This is what is naturally occurring in nature. The most abundant isotope is neon 20. The least abundant isotope is neon 21. So they're all existing in nature. So when we look at the periodic table is basically the sum of all of them. So if this guy is 92%, let's see. If this guy is 92%, its mass is 20. So if we multiply 0.92 times 20, that equals 18.4. If we multiply 0.02 times 21, that equals 0.42. And then if we multiply the other guy, 0.06 times 22, so if we add these guys all up, boy, my number's off. So we'd end up with 19.94 to be the molar mass of the element. Well, my numbers are a little off today. Okay, so by looking at it, we would sit there and have an estimate as to how much of that abundance is. Okay, so we would have to take all of them in consideration to sit there and get it. Okay, you guys understand that? Okay, so in this case, here's an example. So we have the natural distribution of isotopes of boron is 19.9%, and this is boron 10. Okay, it has a mass of 10.0129370. 80%, 80.1% is boron 11, which has a mass of 11.0093055. Calculate the atomic mass of boron. So the way that we would calculate the atomic mass is by looking at the distribution of each of the different isotopes. So we have 19.9% of the boron 10. So we are going to multiply that by, we're going to change it to its decimal form. So it's going to be 0.199 times 10.0129370. Okay, so for right now, we're going to keep 3 significant figures. We'll talk about sig figs later. So basically, we're going to keep 3 digits. So this guy is going to end up being 1.99. And then we're going to multiply 0.801 times 11.0093055. And you're going to end up with, again, we're going to keep 3 sig figs. Eraser. You're going to end up with 8.82. Then we're going to add these 2 together, and that's going to give me my mass of boron. So that's 1, 8. So 10.81. So look on your periodic table. What is the mass of boron? Anyone? Mass of boron?
10.81.
10.81. Okay, so you guys see that the isotopes as a whole, if we take them all into consideration, they should add up to that mass that we see on the periodic table. So what the periodic table gives us, it gives us the average of all of the isotopes that occur naturally in nature. Does that make sense?
Yes.
Yes, no, maybe? Okay, so we could do the same thing here in the case of lithium. Okay, so if we have lithium 6 and we have lithium 7. So in the case of lithium 6, we have 0.0759 times 6.0 1, 5, 1, 2, 2, 4. And then in the case of lithium 7, we have 0.0, I'm sorry, 0.9241 times 7.0160041. Okay, let's go ahead and do that math. Oh, mail. No mail. Sorry. Okay, that's going to be 0.457. And then this guy is going to be 6.483. We add it together. End up with 6.94. Oh. Okay, so what is the mass of lithium? Avenel. 6.94. Okay. Okay, so if you guys had discovered a new element and we have each of the isotopes, if we have the abundance of each of those isotopes, we would be able to sit there and calculate the mass that we would put on the periodic table. Does that make sense? Okay, good. Let's see. Okay, so let's move forward. Okay, so here's an example. So we have all of these different isotopes that exist. So for instance, in terms of hydrogen, these are the two most abundant isotopes. Technically, there's 3, but these are the two most abundant. So we have hydrogen 1 and we have hydrogen 2, right? So in the case of helium, we have helium 3 and helium 4. So in the case of beryllium, we only have that one isotope that mostly exists. In the case of carbon, here we have carbon 12 and carbon 13. Nitrogen, nitrogen 14, nitrogen 15. Okay, and you guys can kind of see so on and so forth. Some of them, they have more isotopes. Okay, so if you're given a table like this, you should be able to sit there and calculate the atomic mass of a particular isotope, right? Good. So in your own time, what I'd like you guys to do, and I'll have a spot for you guys to submit it onto Canvas later today. On your own time, what I'd like you guys to do is to calculate the atomic mass for sulfur using the data on the table. And if you guys can do me a favor, I'd like you guys to do it in terms of, let's say, 5 significant figures. So that means 5 digits should be in your answer. Okay, And if you'll notice, there are 4 digits on the periodic table. So if you give me the answer that is strictly on the periodic table, you know that it's wrong. So you want to make sure that you have your 5 digits. Okay, so if you guys take a look at the periodic table, how is it organized? If you look at it from going from left to right and top to bottom. Okay, so how is it organized? So if we're going from here to here, to here, to here, to here, how's it organized? Anyone?
Atomic number from left to right.
The atomic number from left to right. So it's all organized in terms of the atomic number. Back in the day, when they first started making the periodic table, it wasn't done that way, right? So there's a guy, Dmitry Mendeleev and Luther Meyer. So they decided to organize it based upon, it was initially based upon atomic mass. And then they changed it around to be based upon the atomic number. So the atomic number is always what? What does the atomic number represent?
Protons.
Protons. Okay, so we're organizing a periodic table based upon protons. Okay, so the symbol that we use for atomic number, you'll often see it, it'll be Z. And so you'll often see it throughout chemistry, they'll use that symbol for Z. So that's making reference to the atomic number. Okay, so as you guys can see, it's organized by the atomic number. This is an older periodic table. So in the old days, particularly in the US, we would ignore primarily the transitional metals. So if you look right here, these guys are your transitional metals. We'd also ignore the latinoids, and we'd also ignore the actinoids. Okay, so those guys, I'm sorry, the latinids and the actinids, we would ignore those initially. And so things like that have changed, okay? So because we have a little more information under our belt, we know how to utilize it a little bit better. So this is, again, this is an old periodic table that was used back in the day. That's probably what you guys see on your wall. In the US, we would only pay attention to the ones that had the A. So it would say, this would be group A1, this would be group A2, this would be group A3, A4, A5, because those are the ones that we would come encounter with most of the time. These guys were always special cases, okay? So up top, this way, these are groups. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So all of those guys are groups. These guys going down this way, these are periods, okay? So I'm gonna go to P table again. So on P table, you can actually see up top, the numbers up top are your groups, and the numbers going down the side, these are your periods, okay? So elements that are in a group, they're gonna behave similarly, right? At least in some aspects. So all of these metals in group 1, they're gonna all behave very similarly, right? In terms of reactions. They're gonna be very volatile, they're gonna be very explosive, they're gonna cause things to happen. Elements in group 2, they're gonna behave very similarly, right? And then elements over here, group 13, they're gonna behave similarly, 14, 15, 16, and 17, okay? So they're all gonna behave similarly when they're in reactions. Not the same exactly, but similar, right? How many of you guys got cousins? None of you guys got cousins?
Yeah.
Do anybody say that like you and your cousin act alike or are like in any way? No?
My cousin and I act exactly the same, Dr. Henry.
You guys do?
Yes.
So it's kind of like a cousin, right? So you guys have various traits because your parents were raised very similarly. So they're going to have traits that you guys have in common, right? So that's going to be the same case and with elements that are in the same group. They're not exactly the same, but they're going to act very similar. Okay. Okay, we've talked about this already. You guys are familiar with the atomic number. You're familiar with the chemical symbol. You're familiar with the atomic mass, right? Okay, so let's do a breakdown of the periodic table itself, right? So group 1 metals, these guys that are highlighted in, it looks like yellowish or an orange color. Do you guys see orange and yellow, right? Or orange or yellow, right?
Yeah.
So those guys are alkali metals. Alkali metals, right? They're group 1 metals. They're going to behave very similarly. Like I said, these are alkaline metals, the guys that are in the actual yellow. So these guys, again, are going to behave very similar. These guys are called lanthanoids. These guys are called actinoids. These guys are your transitional metals. These transitional metals, oops, okay. Transitional metals are a little complicated. I like to think of it as that term transition. What does that transition mean to you? Somebody's transitioning. What does that mean to you?
Changing.
Changing. Okay. So these metals here, when they get into complexes, they can change. They're not going to always be the same. They can be different in terms of the number of electrons that they have. And we will be talking about. Okay. These guys are post-transitional metals. So they're also going to be changing. They're considered post-transitional metals because they're located after that line right there. So they're considered to be still changing type of metals, but they're going to change. But they also have various characteristics that they sometimes can act like non-metals, even though that they are metals, okay? So they'll have certain characteristics that they can do. These guys are metalloids. Metalloids are like, they are actually that case where you have metals and non-metals, right? So they have both characteristics of metals and non-metals. And so sometimes they'll act like that metal, sometimes they'll act like a non-metal. Difference between the post-transitional metals and the metalloids is that there are only certain very few cases that a post-transitional metal will act like a non-metal, where a metalloid can do it very frequently, about several different things, okay? We have reactive non-metals, and we have noble gases. The difference between reactive non-metals is that they're able to react. The noble gases are capable of reacting, but on their own, they're not going to want to react, right? Independent, because they're happy the way they are. The only time they ever react with things, and it's particularly certain elements that they will react with, like fluorine and things like that, is when they get forced into it, right? So non-metals, those guys are non-metals. These guys are metals, and these guys are metalloids. Okay? And so looking at the periodic table, can you guys tell me which symbol or which element is in group 7, period 6? Re, rhenium, okay? So it's group 7, period 6. Okay, is it a metal or a non-metal?
Metal.
It's a metal. Is it an alkali metal, an alkaline metal, a lanthanoid metal, an actinoid metal, a transitional metal, or a post-transitional metal? Transitional metal. Okay, let's see. What about, let's see, group 15, period 4?
SB.
Group 15, period 4. 1,5. Period 4. What is it?
Arsenic.
It's arsenic. Okay,
Okay.
AS. Okay, so is that a metal, metalloid, or non-metal?
Metalloid.
It's a metalloid. That's correct. Okay, simple. Yes, no, maybe.
Yes.
Okay, good. Okay. Okay, so these are a list of some of the common elements that you're going to be working with or coming in contact with. So you should be familiar with this. You should be able to identify them almost instantaneously. The best way of being able to identify them is to do all of the homework, stay on top of the homework, use your periodic table constantly, all right? That's it, okay? This is just basically showing you that whole series of those common metals that we're going to interact with. I also like to include gold because AU stole my gold, right? Okay, questions, concerns, Cash? Crayola? Excellent. Okay, so let's see some skills now. Okay, so let's see. We have the element in group 8, period 7.
HS.
HS, hazium. Okay, so we have hazium, right? Okay, so tell me, what is the atomic number of hazium?
(108).
Okay, so we have the atomic number is 108. Okay, how many protons does hazium have?
108.
108. How many electrons does hazium have?
108.
108. How many neutrons does hazium have?
9.
What was that?
169.
169. How did you calculate that?
Mass number minus the atomic number.
That's right. Mass number minus the atomic number. That is correct. Okay. So let's say we have hasmium 281. Okay, how does that distinguish? How is that different from just hasmium? How many, what is the atomic number for hasmium 281?
108.
Still 108, so. Okay, how many protons does it have?
108.
108. How many electrons does it have?
108.
108. How many neutrons does it have?
$173.
So let me make sure I understand this, Julie, since you're the only one that's answering me. It's just me and you in the class. Everybody else just tapped out. So Julie, since you want to pass this class, so make sure that I understand what you're saying. Are you telling me that the difference in mass is only due to the number of neutrons? Is that what you're saying?
No,
That's not what you're saying?
no.
What is it also?
Neutrons and protons.
So it's the addition of neutrons and protons. But the difference here, the difference between that 273 and that 281 is just the fact that I have more neutrons.
Right.
Okay. I just wanted to make sure that I understood that, so that everybody else who don't want to participate are kind of getting it as well too. Okay. Are you guys with me? No, you're not? That's good. Be honest. If you don't get it, let me know, because otherwise I'm going to keep moving on. Okay, so what is it that you don't understand?
You guys understand this?
I thought I heard somebody say no.
They said yes from
They
Avenue.
said yes. Yes, Avenel said yes. Okay. So otherwise, you got to let me know what you don't understand. If you don't let me know what you don't understand, then I can't help you, right? Okay, everybody gets this. You understand it. Okay, so you guys, you have a group discussion that is going to be due on Friday. This is going to help you with the test, right? There's a question on the test, and I always ask, it's going to actually help you very much on this test. So it's going to be a group discussion. You guys are going to be put in groups. So you guys are going to interact with each other in groups via discussion. And then you guys are going to fill out a table, and you're going to submit that table as a group. I have to adjust it. Somebody had already did it for me. It was technically due on Monday or last week or something like that when it wasn't supposed to. Somebody got ahead of the game. Okay, so I'll delete that one and resubmit it. Okay. Okay, I have a question now. So let's see. Let me clear this. If I have chromium, $49. Okay, chromium 49. What is the mass number of chromium 49? A stands for mass number.
49.
49. How many electrons does chromium 49 have?
24.
How many protons?
24.
24. How many neutrons? 25. I heard somebody say it. I heard 25. That's an O. Okay. Let's see. What is the weight of chromium? Of chromium 49?
Is that also 49?
That's also 49. Yes, because it's the new mass of that particular isotope. Okay. So here's a question. Is chromium 49 an isotope?
Yes.
Okay. Piece of cake. I heard somebody say yes. Yes, it is an isotope. Simple, not too hard. Good. Okay, I'm going to clear the screen. Okay, so the next thing that I'm going to talk about is ions. Okay, that's an S, although it looks like a 5. Okay, ion. Ions are just charged elements. Now, the way that they get charged is it's sort of, it's not too difficult, it's pretty simple. But you got to have a little bit of an understanding about the periodic table and things we kind of talked about and remember some of the things we talked about. Now, I told you guys earlier that these guys are noble gases, right? And I told you that they're considered noble because they are happy, right? The reason why they're happy is because they have their outer electron shell full, okay? So they're what we call fat and happy. So they don't want to react because of that. Now, all the other elements on the other side of those noble gases, they're not happy because they don't have that outer shell completely full. So they want to be like the Joneses. They want to be like the noble gases. So all of the other elements want to try to find a way to be like the noble gas, meaning that they all want to sit there and have the same number of electrons as a noble gas, okay? So for instance, we have fluorine here. Fluorine wants to be like neon because neon is the nearest noble gas. So for it to be like neon, how many electrons would fluorine need to gain? How many electrons does fluorine have?
9,
It has 9. How many electrons does neon have?
10,
So how many electrons does fluorine need to gain? 1. Okay, so fluorine needs to gain 1 electron to be like neon. Okay, what about chlorine?
Seven? Is that
Chlorine?
how you do that? Or would it still be one?
It would still need to be 1, right? Because and it wants to be like the nearest noble gas. Who is the nearest noble gas?
Which is argon?
Argon, right? So argon is the nearest noble gas. So it needs to gain 1 electron to be like argon. Did you guys see that?
yeah,
Okay. So what about nitrogen? The nearest noble gas. So if you look where nitrogen's at, the nearest noble gas is neon because it's 1, 2, 3, right? If we lose electrons, 1, 2, 3, 4, 5, right? You always want to go the easiest way, shortest distance. Okay, so nitrogen, how many electrons does it need to gain to be like neon?
3.
3. Okay, so let's sit there and write this down chemically so we can understand it. So nitrogen needs to gain, you said 3 electrons?
Yeah.
So nitrogen plus 3 electrons, that's going to yield an ion. This guy is called an anion. I'll type it out here in a second. But now it's going to have 3 minus charges. So we write 3 as a superscript and we put a minus to let us know that it's 3 minus charges. Okay, why is it 3 minus charges?
because it needs 3 electrons.
Because it needs 3 electrons, and we know that electrons are negatively charged, right? Okay, so this guy is called a cation. I mean, sorry, not a cation, an anion. anion. Okay, can you guys see that?
Yes.
Okay. Yeah, we're running out of room to write stuff. Okay, so this guy's an anion. Now, if we go over on the other side of the periodic table, we get something like magnesium, Mg. The nearest noble gas to Mg is what? It's right here. This is where it's located. So if we go back, we got 1, 2 to be like neon, or we can go 1, 2, 3, 4, 5, 6 to be like argon. So if magnesium is like us, would you prefer walking 2 blocks to a store, or would you prefer walking 6 blocks to a store?
2.
2, right? Because we're naturally lazy. So the elements themselves are also going to be naturally lazy. They're going to try to find the quickest way to get to a noble gas. Okay, in this case, it's by losing 2 electrons. So the way we would write that chemically, we'd write Mg 2 plus plus 2 electrons. That's an E. Okay, are you guys with me so far? So why is it 2 plus?
Electrons are negatively charged.
That's right, because electrons are negatively charged. So if I have something that is 0 normally, and I remove 2 negatively charged things, that means that what's left is going to be 2 plus. Make sense? Okay, so yesterday, I can't remember who it was, but she sits in the front row at Avenel. She asked me, why do things react? Okay, do you guys remember that? Remember that question yesterday? Okay, so, and what did I say? Okay, so you don't have to answer. I'm going to ask you guys a question, right? This is a hypothetical. Okay, let's say you have these twins, right? One is a doctor and one is a crackhead. Okay. Now, you know, the doctor, he's been a doctor for several years, got his life established, he got cars, he had everything. And then the other one is a crackhead, right? He's been a crackhead for years, always been a crackhead, total crackhead, totally unstable, pops off, you know, the whole 9 yards. Okay, so now they're both very attractive. They're both wooing you, right? Which one would you go for? The doctor or the crackhead? Did somebody say the crackhead?
Some people are saying crackhead, the doctor.
I would hope if you did say the crackhead, you might want to leave right now. I can set you up perfectly. There's tons of people out on the streets right now that'll help you out. Okay, so most of us who are logical are going to go for the doctor, right? Why are we going to go for the doctor?
For that money, you could save your life. They're saying for the moolah.
For the money. Okay,
Yeah.
so ultimately it boils down to what we call stability, right? Because we know that a doctor is always going to have a job. They're going to be able to take care of us. They're going to be able to sit there and help us throughout life. Where the crackhead, we may end up in the grave messing around with the crackhead, right? Okay, so we know that that represents stability, right? So the reason why reactions occur is because we want stability, right? So reactions want to be stable. They want to be like the noble gases. And there are only a couple of ways that you can be like the noble gases. There are 3 ways, right? Either you can give up electrons, or you can take electrons, or you can share electrons, okay? So that's how you're gonna be like a noble gas, okay? So you're gonna give, take, or share, okay? So there are a couple bonds that we need to sit there and talk about. So now these guys are called ions, right? So this guy was an anion. I didn't tell you what this guy was. Let me tell you what this guy is. Move on. This guy is called a cation. Okay, a cation is positive, right? You know, cation, positive, right? You guys get the joke? Ba-dum-bum. Cation, positive. Okay, nobody ever laughs at my joke. Okay, so cations are always going to have a positive charge associated with it. So this guy is the magnesium ion. An anion is always going to have a negative charge associated with it. When we make an anion and it's for an element, we put "ide" at the end. So this guy would be called nitride. So this would be the nitride ion. Let me write that down so you guys will know. So nitride. So we drop the OGEN and we put IDEN. These guys, this one here is going to just be called the magnesium ion. Okay, metals, most of the time, majority of the time, are going to form positive ions if they form ions. Okay, so magnesium is always going to be positive. It's always going to be positive too. Okay, non-metals, most of the time are going to be negative. Now, there can be some exceptions. Okay, because if you guys take a look at this, we have carbon, right? Carbon is like right there in the middle, right? It could be like neon if we gain 4 electrons, 1, 2, 3, 4, or it could be like helium if we lose 4 electrons, 1, 2, 3, 4. So carbon technically can go either way, right? Again, we talked about it yesterday. Carbon is a little bit of a whore. It can swing both ways, okay? So are you with me so far? Okay. So now let's talk about these transitional metals. Now, transitional metals and the post-transitional metals, and sometimes these metalloids, right? So these guys, and I should say actinoids and lanthanoids, all of those guys there. So we'll say, see if I can highlight this. So kind of remind you, so we have these guys here. Oops. So we have the lanthanoids, we have the actinoids, we have the transitional metals, and then sometimes the metalloid. Now, these guys, they can have changing charges, right? So they're going to be cations in most cases. I should say these guys, in most cases, they're going to have positive charges, but the charges that they have is going to depend on who they're with, right? So that's the part of them changing. So they don't always have to be a +2 or +6 or +7. It just depends on who they're associating with, that they're going to have a charge associated with it. So they balance out their charges based upon the partner that they're going to be hooking up with. Okay, so let me give you an example. It doesn't quite make sense, but I promise you it will in a second. Okay, so if I have Okay, so these are two compounds. These guys are going to be called ionic compounds because it's going to involve ions. Okay, so when you have a metal and a non-metal coming together to form a compound, that's going to be an ionic compound. Okay, now the way that they come together is by charges. So one of them is going to be taking electrons and one of them is going to be giving electrons. So in this case, who's going to be taking the electrons?
Non-metal?
The non-metal. So the non-metal always is going to be taking the electrons, okay, when you have a metal and a non-metal together. So how many electrons is oxygen going to take? How far is it from being a noble gas?
Two?
It's two. 1, 2, right? So oxygen is going to have a -2 charge. Now, the metal has to balance out that charge on oxygen. So what would be the charge on tungsten? So do you guys know what I mean by balance out?
Cancel each other out?
Cancel each other out. So what would be the charge on tungsten for it to cancel it out? In other words, it actually has to add up to 0.
So 2 positive charge.
That's right. So it's going to be a 2 positive charge. Okay. So we have a 2 positive and a 2 negative, and they come together and they form this compound. This compound has a total of a 0 charge. Each of those ions are charged, but they come together to make that compound a neutral charge. So that's what ionic bonds do. You come together to try to neutralize each other, right? Okay, so you're using the opposites. So how many of you guys dated in high school? Raise your hand. So you're gonna tell me in Avondale, none of you guys ever dated. I saw you guys making ooh eyes at each other. Don't lie. So,
No.
okay, so none of you guys ever dated.
They're pure
I'm blowing
souls.
so much
Dr.
smoke up my
Henry.
butt. I can't believe that. Okay, what about Kalinga? How many of you guys dated? I would hope that some of you guys are, I know that some of you guys are married. I would hope that you guys dated before you guys got married. Did you guys do that? Okay, nobody dated, huh? What about NDC, Fireball? Any of you guys dated? Well, you guys have such boring lives. Okay, so let me tell you a little bit of a story, right? Okay, and you guys can tell me if you're late since you guys are not going to let me into your personal business. I understand that, okay? So, if do you guys know, we'll say if you guys know of anyone, right? What is dating? Okay, so if you guys know of anyone that you've ever come across that this happened to. So they meet this boy at school or this girl at school, and they're a good kid, you know, and everything like that. They're the good kid, right? And then they meet the boy and they're like, they go home to their mom and dad and they're like, Mom, I met the best boy ever. He is so cute. He is so charming. Oh my God, I'm so in love. I love him, Mom. I love him, right? And Mom says, oh, baby, you know, who is it? Who is it? I want to know, right? She's all into it and everything. And you say, Tommy Jones. And your mom looks at you and says, Tommy Jones, from the Jones family down the road? The crack dealer? The hustler? The little gangster? No. You're my baby. You're not dating that. You're a good girl. You stay away from that boy.
Yeah.
And then what did she do? Tell me, what does she do? Does she stay away from the boy? No. right? She sneaks around and dates him anyway, right? Behind mom's back, right? Why did she do that?
Is she disobedient?
Because she's disobedient, and ultimately opposites attract, right? The first thing that she's thinking, she's like, I can change him, right? I can neutralize him, right? She can balance him out. Okay, so here, in terms of an ionic compound, that's what's happening. You have the good girl and the bad boy, and they have to come together and balance each other out. Otherwise, there won't be a reaction. Okay, you know, something else will happen. You get a threesome started or something like that. Okay. Okay, so you want to make sure that you're balancing out that partner. So that's the reason why this guy has to be 2+ when this guy is 2-. So if I have 2 oxygens, each one of those are going to be 2-, right? So then what must be that metal? That tungsten must be what charge to balance out those 2-. Those two 2-. What was that?
4 positive, right?
That's right, 4+. Okay, are you guys getting that?
Yes.
Okay, Avenel, are you guys getting it? Let me see them heads nod, because I can see you. Okay, you raised a hand. You had a question?
Oh, no, it's thumbs up.
Okay, thumbs up, got you. Okay, okay, so now those are called ionic compounds. Now, the way I kind of like looking at this, right? Also, another way of kind of remembering it, what's going to be forming ionic compounds. So you have your non-metals and you have your metals, right? So your non-metals, when they interact with each other, they're going to form what we call a covalent bond. They're going to share electrons. Now, the reason I like to use this analogy, right, is because it helps me remember that things are going to be shared in some cases and things are going to be taken and given in the other cases. Now, let's say you saw this really unique bicycle, right, or a motorcycle or whatever, unique motorcycle. Now, your neighbor has one, and then this guy, you know, 300 miles away, a different town has one, right? And let's say, I know that none of you guys are criminals or anything like that, but let's say you were a criminal, right? Would you steal it from your neighbor, or would you steal it from the guy that's 300 miles away from you? Right? I would hope you're smart enough not to steal it from your neighbor, because I think he would know if you just put the motorcycle in your garage and say, oh, look at my new motorcycle, right? He'd be like, what the hell? You just stole my motorcycle, and he called a poop on you, right? Okay, so in that case, you're going to take away from that guy who's on the other side of town. You're the non-metals, here's the other side of town. So you're going to be taking from them. So you're taking electrons from those guys, right? They're going to be giving up those electrons. Where the ones that are on the same side of town as you, you're going to share, right? You're going to share electrons. So these guys, these non-metals, are going to be sharing electrons. Now, sharing electrons, they form what we call a covalent bond. Okay, you guys with me so far?
Yeah.
Okay, so we have ionic and covalent. Okay, covalent is sharing, ionic is taking and giving. Okay, okay, chapter 11. Okay, so we're going to start off with talking about electromagnetic waves or electromagnetic radiation. Okay, so energy in the form of electric and magnetic waves. So we basically are transmitting energy in various different ways. Right? So like light rays are basically, can you guys hear me? Can you guys see the screen?
Yes.
Okay, I just want to be sure. Okay, so light waves are forms of energy. Right? So do you guys, when the sun shines on you, do you feel it?
Yes.
Yeah?
Mhm.
No, it doesn't. You don't feel it. You don't feel that energy on a really hot day, sun beating down on you. You don't feel anything. Okay.
I do.
I know I do. All right. So those are forms of energy. So we know that light can be a form of energy. Now, light actually travels, right? It has a speed that's associated with it. The speed of light is 3.00 times 10 to the 8th meters per second. Okay. So, and light can actually travel in waves, like the ocean waves, right? And I'll show you that here as an example here in a second. Okay. So light has what we call, it has a dual characteristics. It has that wave characteristics, and it also has a particle characteristic associated with it. Okay. Now, when we talk about light, there's various forms of light, and there's also various forms of what we call electromagnetic radiation. Some of those are gamma rays, X-rays. You guys heard of gamma rays, the Incredible Hulk? You know, they got gamma rays, and that's what made him the Incredible Hulk. X-rays, you guys go to the doctor, you broke your arm, they take an X-ray, right? You guys, infrared light, you know, be able to see in the dark and all that stuff. You're familiar with that? Microwaves, right? You guys cook your food in the microwave. You guys listen to the radio, hey, you know, right? So all of those are waves. All of those are forms of energy, right? And the difference between those waves, the difference between radio waves and light waves is not the speed that they're traveling, but it's actually the wavelength, right? The wavelength is defined as lambda. You guys see my screen down here? This funny looking, let me circle it. Having a little trouble finding mine. So this guy is lambda. So that represents the wavelength. So that's the distance, let's say a cycle of a single wave goes. Have you guys ever been to the beach and saw the ocean wave? The ocean, yeah. So if it was a very, very short wave, it's going to have a small wavelength. If it's a long wave, it's a really long wave, it's going to have a large wavelength. Now, speed of light is always going to be 3.00 times 10 to the 8th, right? But the difference that's going to be changing is going to be the wavelength. And if the wavelength changes, that means that the frequency has to change. This guy here, this letter, it's like this. It's called nu. It's the Greek letter nu. Now, nu represents the frequency. So wavelength times frequency equals the speed of light. That's always going to be the case. So if we
Dr.
have,
Henry, can you get closer to your screen, please?
can I get closer to, can you hear me now? Are you having trouble hearing me? Is that what you're saying?
Can you guys hear him?
Yeah, there you go.
We
Barely?
can barely,
speak up.
yeah.
I can speak up.
Okay.
I just didn't want to yell in your ears, you know, so I can get loud. Okay, so I was saying that nu, this symbol down here, that looks like a funny V, nu is frequency. And lambda is wavelength. Lambda times nu equals c, speed of light. So light, if you guys look at white light, like the light that we get from the sun and the light that we get from being in the classroom, clear light, that really is a combination of all of these different colors of light all together, right? So green light, which is in that white light, green light is about 560 nanometers. That would be the wavelength for green light. Red light is about 700 nanometers. Okay, so now you guys are probably saying, what's a nanometer, right? Anybody want to know what a nanometer is? So you guys heard of a meter before, right?
Yes.
Okay, so one meter equals 10 to the 9 nanometers. And the reason I remember that is because let's just say, sorry, 9 starts with an N. So I know that nanometers, 10 to the 9 nanometers equal 1 meter. Okay, so since this guy is in meters, if I'm going to use this equation, I have to change my nanometers into meters. Okay, so I'm going to go to a whiteboard. So we have this equation, C equals lambda nu, where we know C is going to be equal to 3.00 times 10 to the 8th meters per second. So we're trying to find out for, let's say, green light. So green light, it has a wavelength of 560 nanometers. Now, if I'm going to use this, I need to make sure that my units are going to be the same. So I have to change my nanometers to meters. So if I have 560 nanometers,
Guys, quiet down, please.
how many nanometers will equal a meter? How many nanometers will equal a meter?
10 to the 9.
Equals a meter.
So 1 meter?
10 to the what?
10 to the 9. Okay, so if I look at this, nanometers are going to cancel out, and I'm left with meters. And so I get 5.60 times 10 to the, this is dividing, so that would be 10 to the minus 7 in scientific notation, meters. Okay, so if I'm going to use this equation here, I'm going to go ahead and plug this guy in for C. So I have 3.00 times 10 to the 8th meters per second is going to equal 5.60 times 10 to the minus 7 meters. Okay, times nu. Okay, so if I want to solve for nu, I'm going to divide both sides by 5.60 times 10 to the minus 7 meters. because we know in math, what I do to one side, I got to do to the other side of the equal sign, right? You guys remember that. So then I get, I'm just going to bring new on this side to make it easier for me. So new equals, we plug it in. And I'm only going to keep 3 digits. So it's going to 3.36 times 10 to the 14. And if I look at the units that are going to be left over, I get rid of meters. So I'm going to have the units of 1/seconds left over. That's an S for seconds. Okay, so 1/seconds also means hertz. Which the symbol for hertz is Hz. Okay. Okay, are you guys with me so far?
Yeah.
Okay, so ultimately, if we look at this as the wavelength increases, the frequency has to decrease. I'm going to show you that on a table here in a second. As the frequency increases, the wavelength has to decrease. So these guys are called inversely proportional. Okay, so because one is going up, then the other one has to go down. That's the only way that C is always going to be the same value. Okay, so let me show you that. You switch gears. Okay, so here, if you look up top is the frequency, here is the wavelength. So wavelength is small. As the wavelength increases, the frequency decreases. As the frequency increases, the wavelength decreases. Okay? So in here represents that wavelength. So as we're increasing the wavelength, the frequency is decreasing. And this gives you an idea where everything's at. So here, these are our gamma rays. In this region right here, here are the X-rays. These are the UV. This is visible light. That's that visible spectrum. These are infrared waves. This is your microwave. These are your radio waves. And this is your long radio wave, right? And this gives you an idea how far apart those waves are, right? So these guys are really, really small. And then these guys are, in terms of X-rays, in that area, these are about the size of atoms. And then UV waves are going to be about the size of a virus. Infrared waves are going to be about the size of bacteria or animal cells. Microwaves are about the thickness of a CD. And then also the width of a CD. Radio waves is about the size of a dog. Okay, so you guys get an idea of how far that is for that wave. So when we're talking about that wave, it's from peak to peak, what we define as a wave. Peak to peak or trough to trough. Okay, peak to peak, trough to trough. Are you with me?
Yes.
Good. Okay, so now the let me take a step back. So this here is the visible light spectrum. So the spectrum represents all of the different colors. We're actually separating them individual colors. Now, if you look at it, these colors are all blending into each other. So that's considered to be a continuous spectrum because you're getting blending in. We can also have what we call a discrete spectrum, right? Where you get individual lines of the spectrum, okay? So line spectrum, continuous, okay? And remember, I just told you that light has a dual characteristic. It has a wave particle duality. And so photons are basically just bundles of energy that the electrons are going to be basically emitting, okay? Or light that the electrons are going to be emitting. So a photon of light is just that energy that's being released, okay? So this here represents a wave. So the wavelength from peak to peak, right? So this guy is a wavelength, and it's a large wavelength, so its frequency is small, where this one is a small wavelength, and so its frequency is large. Okay, are you guys with me so far?
Yes.
Okay, so this is just showing you again that continuous spectrum. This here is showing you the discrete line. Okay, so here white light gives us that continuous spectrum. Here, this is basically an element. This is just hydrogen gas in a tube, and it's being charged up with energy, and then so it's containing that energy. These electrons are basically picking up that energy, and it shoots them up to another energy level, and this energy level is then being dropped down, and so you get energy being released, and so you're getting each individual electron emitting, or I should say individual electrons emitting light being set up in different energy levels. And I'll show you another figure of that in a second. Okay, so this here represents the line spectrum of hydrogen compared to helium, compared to neon. Every element has a discrete looking line spectrum. They're not going to look anything alike from each other. Okay, so this brings us to this guy named Bohr. Bohr basically has a model for the hydrogen atom. He said that basically you have in the nucleus, you have an electron. In the nucleus, you have your nucleus, and you have the electrons orbiting around the nucleus. Now, this orbiting around the nucleus, there's energy levels that are associated with the different orbits around that nucleus. Okay, and he says that if you put energy into that, it's going to shoot that electron to that different energy level. Okay, so this process is called quantization, right? And so that's how we get the term quantum, right? So quantum mechanics or the quantum theory. Okay, so that discrete line set is that quantization, right? Or quantizing, compared to the continuous where things are going from point to point to point. Continuous. So Bohr basically hypothesized that we have the discrete energy levels that we can pop up to. Okay, to kind of put this in perspective. So this here would be that continuous case. This would be an example of quantizing those steps. So each step represents a different energy level. This here, this is that nucleus. This would be that first energy level. This is the second energy level. This is the third energy level. This is the fourth energy level. Okay, so if you look on the periodic table, these periods here, these guys, the periods represent each of the individual energy levels. Okay, and we'll get to how that's all going to be tied up together tomorrow. Okay, how are you guys doing so far?
How are you guys doing so far? He asked. You guys got this? You understand this? Not so bad.
Okay, good. So I can move on. Let's make it a little bit harder.
you have time, go to upgrade today. I have upgrade from 3 to 6. You don't have to be there at 3. If you have work or whatever, you can join later. Wait, where's from 3 to 6? It's on the syllabus. You just click on my name, it'll send you to the link. I need help with my math. Okay, yeah, go to upgrade and I'll help you.
Okay, so a long time ago, there's this show called Quantum Leap, right? So a quantum jump is basically the electron going from one energy level to another energy level. And the fact that you can go from one energy level without going to the second energy level to the third energy level, you can actually just go from the first one to the fourth, okay? So in other words, I can start here at the second one and I can shoot up all the way to the fourth energy level without having to go through each of the individual ones. That is called a quantum jump. Are you guys there? Are you listening?
30 minutes. Okay, Dr. Henry?
Yep.
Can you hear us?
I can hear you.
Okay. You guys, he's still lecturing. He's not done yet.
I wasn't done yet. I want to get one more thing before we go, right? So the next part is where we start off at, that's called our ground state. How many of you guys have little sisters or little brothers or son or nieces or nephews? Any of you guys have any of those things?
Yay.
What happens when you feed them a whole bunch of candy?
They get hyper.
They get hyper, okay? So when we feed an electron a whole bunch of energy, right? It gets hyper. It shoots up to another energy level. It goes to a higher state. Now, what happens to your nieces or nephews or kids when you feed them all that sugar and you wait a couple of hours later?
They die down.
Oh, they crash, right? Then they're all sleeping and they're, oh God, I'm so tired, right? Okay, so that's the same thing that happens. So we shoot it up, we get it in an excited state and it drops down in energy. Now that drop down in energy means that energy is being released, right? So that means that since energy is being released, we actually get a photon emitted. So as a result of that, we get light, okay? So here's our ground state. We put some energy in, energy is absorbed, it shoots it up to this new energy level. And then when it drops down, we get light, right? You guys see that little light beam going out there? So that's the reason why, you know, we get light emitted. So when you guys, some of you guys who did lab today, you saw that. Other of you guys will see it tomorrow, okay? So we're gonna stop right here and then we'll start talking about those quantum numbers tomorrow.